All right, good morning, everyone. Can you all hear me in the back? We're good? Okay. All right, does anyone have any questions before we get started? All right, cool. Then let's summarize everything that we talked about last lecture. Or not everything, but what we talked about last lecture with our reductions of our alkynes. So if I had hydrogen and palladium on carbon, what was the product? Went from an alkyne to alkane. All right, what if I had hydrogen in Lindlar's catalyst? So having that quinoline with the palladium and, yeah, the cis-alkene, thank you. That's trans. All right, and then if we have our Birch reduction having that sodium metal and liquid ammonia, transalkene. Perfect. So those were our reductions of our alkyne. And remember that hydrogen, when you have H2 gas, it is always in excess. So there's no way to try to limit the equivalency there. It always is in excess. So when we look at our normal addition reactions, they're going to be the same general reactions as our alkene additions. So we're going to have the same reagents. We just have one more pi bond, so additional reactions could occur, or we're going to have a couple of exceptions where we're going to get a different product. But first of all, let's talk about our hydrohalogenation. So for the hydrohalogenation, which mechanism did that go through? What were our 4 alkene addition mechanisms? Carbocation, syn, anti, oxidative cleavage. Okay, so out of those 4, which one did we use the strong acid with? Carbocation. So it's going to be a carbocation mechanism. And what was the regioselectivity? Was it Markovnikov or anti-Markovnikov? Markovnikov. So when we had it with an alkene, we got our halogen in the middle, the hydrogen on the outside. So when we have our alkyne, we're going to do the same thing. If you have one equivalent, then you only have one hydrogen and one halogen to add. So you only do one addition. You're still getting the halogen on the Markovnikov product, or sorry, on the more substituted side. So it's still being described as Markovnikov regioselectivity. It's just if you only have one of them, you can only do it once. If you have excess, then you do it multiple times. So you go through that same initial alkene, but remembering that that alkene is reactive to this reagent, so I can do it again. So I add 2 hydrogens and 2 halogens across that alkyne. My mechanism is the same as my carbocation mechanism. It's going to be pi bond, attacks the hydrogen, kicks out the halogen. We make a carbocation. Yes, it is not stable, but it is still going to be formed for a very short period of time. So very rapidly, that halogen then attacks that carbocation to give us this product. So it's the exact same mechanism as the alkene addition carbocations. It's just you have an extra pi bond. Cool. All right. So when we do our hydration, these are going to lead to different products. Anytime you're adding an alcohol, we're going to see a different product formed. So when we do this hydration, normally, if you have that alkene and you add that sulfuric acid and water, you would get the Markovnikov alcohol, right? You get the alcohol on the more substituted side. So for our hydration with strong acid, we're still going to do the same thing. It still is that carbocation mechanism. It still is Markovnikov regioselectivity. The difference is that our intermediate is that enol. What do we know about enols? What do I know about having that alcohol directly attached to my alkene? Is it stable? No, it was really unstable. So what did it do? This is that one synthesis question on the exam. Tautomerized, yes. It tautomerized to the carbonyl. So before I even get a chance to do any additional additions, before I can do anything else, this will tautomerize. It will become a ketone. This is the product. This is our product regardless of the number of equivalents. It doesn't matter if you have excess water, because as soon as you do that first addition, you make that enol. That enol is so unstable, it immediately tautomerizes to the ketone. And then that ketone no longer is a carbon-carbon double bond, so it can't do the addition anymore, right? Because it's not an alkene anymore. Yeah. Yeah, so the net transformation is this hydrogen is going to end up on the end carbon, yeah. So we're going to do that mechanism right now to illustrate that. But yes. Okay, so let's show that mechanism. So it starts out just as a normal carbocation mechanism of pi bond, attacks the acidic proton, we kick out the conjugate base. I make the most stable carbocation possible. You get that hydrogen sulfate plus water. Water is our nucleophile, because remember that hydrogen sulfate is so resonance stabilized, it will never be a nucleophile or base. So water attacks in. I get that positively charged oxonium ion. So I just need to do acid base in order to get it neutral. So water is going to deprotonate. And we get our enol. So that enol is going to then attack that acid. But what's happening is instead of it just being the pi bond attacking on its own, it's going to be this oxygen comes down and is going to push out that pi bond, right? Because it's not a normal alkene. I have that polarized bond there, so that oxygen with the lone pairs is going to fall down and push out the pi bond. And then water just deprotonates in order to get it neutral. So this is the tautomerization. Going from the enol to the carbonyl. The reason why this arrow happens, why the oxygen's lone pair falls down at the same time, why it is all concerted, is going to be, we need to think about so why do we have that arrow, that asterisk arrow? We have to think about the reaction. Oh, that looks weird. If I just imagine that alkene acting like a normal double bond. So if I have that alkene acting as like a normal double bond to take that acidic proton, right? So without that extra arrow. We get here, right? We would get that carbocation that is right next to that alcohol. That carbon does not have a full octet. So that is not the major resonance contributor. That is not the most stable form for that structure. The most stable resonance form is where we get that lone pair came down. So the reason why is because we're looking at that I have an incomplete octet when I have the carbocation. So even though I am giving a positive charge to the more electronegative atom, that usually is like ooh, we don't want to do that. But the most important thing is filling our octets, especially for carbon. Carbon wants a full octet. So if you get a resonance structure where carbon can have a full octet, that is what we are doing. So instead of it being this stepwise, where we make our not major resonance contributor, we include this arrow from jump. We start with that arrow pushing the pi bond out, right? So it happens all in one go so that we end at our major resonance contributor. That's why this is one step instead of two, or instead of one step with a resonance arrow. You just do the two arrows together to get to the major resonance contributor. Does that make sense? Okay. This is something that all enols will do. All enols will have the lone pair falls down and it pushes out the pi bond. So this is like, you'll spend a month or more in Orgo 2, where you're just gonna draw this over and over and over and over and over, because this is what they do. The lone pair falls down and it pushes out the pi bond because we want to avoid that minor resonance contributor making that carbocation. Any questions about that mechanism? Okay. Also, since we are in acid, there's one other thing I want to point out. Since we are in strong acid, you do not deprotonate first. Right? So removing that hydrogen off the oxygen, we don't do that because we need to have the positive charges because we're in strong acid. We keep things protonated or neutral, right? We're not going to form anions if I have strong acid around. You're not going to make a strong base if you have strong acid around. So we're going to form that oxygen with the positive charge and then deprotonate, because in acidic conditions, you keep positive charges or neutral on your carbon scaffold. All right, so when we talk about our hydroboration oxidation, what did that do with our alkenes? What product did we make with an alkene? So if I have R with my alkene, and I'm doing the same reaction, what's my product? What functional group? Alcohol, yeah. Specifically, is it going to be a primary or secondary alcohol? Primary, because it is anti-Markovnikov. So this was the only anti-Markovnikov mechanism that we've talked about so far. And we said that the reason why it was anti-Markovnikov is because that first addition step is a syn addition. And we need boron to go on the side where it has more space. So sterics are what are controlling the regioselectivity here. So when we did our alkene addition, you ended up with the primary alcohol. You ended up with the alcohol on the end, on the less substituted side. So when we do it with our alkyne, we're going to do the same thing. You're going to get the alcohol on the end, but remember, the second you make an enol, it's the second you put an alcohol on an alkene directly, it tautomerizes. And in this case, it will become an aldehyde. If you have an R group on both sides, then there's nothing to control the regioselectivity. You would get the carbonyl on both sides, right? So this is just specifically for our terminal alkynes. Same thing with our hydration. It's where you have a difference in substitution patterns. So the terminal alkyne goes to the aldehyde. Usually, you aren't actually using BH3. You will use a different version of BH3. So most commonly, you'll have some sort of hydroborane that has really bulky R groups. So you still need the one hydrogen in the boron. That part is still going to be the same. But normally it'll have bulky R groups. The reason why is because your alkyne is linear, right? It's just a straight line. So the difference between the left and the right side actually isn't that significant in terms of sterics for just a BH3, for a little molecule like little BH3. So in order to improve the regioselectivity, you typically will have bulky R groups instead. So it'll either be like a cyclohexyl or it'll be some adamantyl or whatever. You get R groups on there that make it bigger. That way it makes sure that your boron ends up on the end. I'm cool if you keep using BH3. I'm mostly pointing this out so that if you see this reagent, you don't go, what the heck is that? It is the same thing as BH3. It's just improving your regioselectivity. When we do our halogenation reaction, now we are going to have our equivalency become a concern again, because we're not making enols, we're adding halogens. So equivalency will control how many of those elements we add. So in the case of having just one equivalent of our halogen, we're going to just add 1x on each side. Which mechanism did the halogenation go through? Carbocation, syn, antioxidative cleavage. Anti. So it was that anti mechanism. It went through that onium ion intermediate. So what that tells me is I'm going to make a trans product. I need to get my halogens on opposite sides because it is the anti-mechanism. If I have excess, well, we're still going to go through that middle alkene. But because that is still an alkene, it can keep reacting and just do the reaction again. So you just get a total of 4 halogens added across. Yeah. So the wedges and dashes for this structure, no, because it is sp2 hybridized, so we don't do wedges and dashes when we're on double bonds. And here, because these are not chiral centers, because you're adding 2 of the same element, so you have 2 groups that are exactly the same, you again don't have wedges and dashes. Looking at our oxidative cleavage with our ozonolysis, we're going to see the exact same thing. We're still going to do oxidative cleavage. The difference here, though, is that it isn't as, like, I don't need to have an oxidant in the second step, because the intermediate we're going to make is going to be so unstable, it's going to just like keep breaking down and it's going to give our carboxylic acids. So if you have an internal alkyne, it doesn't need hydrogen peroxide anymore. It's going to make my 2 carboxylic acids. Bless you. So it'll just cut it in half, carboxylic acid on each side where you originally had your alkyne. If you have a terminal alkyne, so the alkyne is on the end, you have a hydrogen on one side, we're only going to actually see one product. We will only see the one carboxylic acid because the other product, that formic acid, this is going to continue to get oxidized under ozonolysis conditions to become carbon dioxide gas. So you'll see on a terminal alkyne, you'll see bubbling out. The bubbles indicate the production of gas. So for a terminal alkyne, you see that carbon dioxide bubble out. So you get one carboxylic acid that you see, one organic product, and one inorganic, one not organic product of carbon dioxide gas. Okay. Are there any questions about those doing normal addition reactions with our alkynes? All right, sweet. So additional reactions that we're going to have are cross-coupling reactions. So the reason I'm going to tell you about these cross-couplings, even though I'm not going to require you to know the mechanisms, and I'm not going to ask you any specific questions on the final exam, but the reason that I'm telling you about them is because they actually are extremely powerful reactions. So if you want to use them in a synthesis question on the final exam, you are more than welcome to. It can cut down the number It can cut down the number of steps that you need to take in a reaction when you're proposing a synthesis. So cross-couplings can be really synthetically useful. I will not require you to use them though. So I will always have an alternative set of reactions that will get to the product on the synthesis questions on the final. But if you want to use cross-couplings, you're more than free to. So that is just something to be aware of. So you don't need to know the mechanisms, because these are going to be inorganic mechanisms or organometallic mechanisms, and they're going to be catalytic. So they're going to require catalytic cycles. It is beyond the scope of this class. We do not have time to get into the details of everything that's going on with it. You'd have to know more about metals and how metals react. So you don't need to worry about the mechanism. You can just know and appreciate how nice they are. So remember that we cannot do an SN2 reaction on sp2 hybridized carbons. And that vinyl cation, although we did show it in the addition reactions, that is very unstable. So having that positive charge on a double bond, that is very unstable. It is very hard to form. It is unlikely to form. The only time that we drew that was with our acid catalyzed mechanisms, and to be honest, our mechanisms are probably not 100% accurate because this is so unstable. There's probably something else going on, but I just want you to draw it like a normal carbocation mechanism, right? So when we were drawing this thing, this step probably isn't that simple. So usually this step will also require some sort of like mercury to facilitate it. So like when you do that like oxymercuration, demercuration, that can help facilitate this reaction because you don't actually get a true carbocation on the double bond. That is so unstable. It is very unhappy. I'm okay if you draw it, again, because I want you to keep it simple, but just be aware of like, any other time you see this, I want you to cringe. I want you to see that and be like, that doesn't feel right. The only time you can do it is with the alkyne, with the carbocation mechanism, with the strong acid. Every other time, don't do it. It is very unstable. So instead, we found that metals are going to be able to do this instead of a substitution on the SN2. Metals can do insertions, right? Which we've already seen, where if you had a vinylic bromide and you added magnesium, we made our Grignard, right? Because it happened via an insertion reaction, where that magnesium's like, let me just scooch on in here, and it just pushes them apart, right? We saw that metals can do this, that metals have a little bit more freedom when it comes to sp2 hybridized atoms, or sp as well. So when our double or triple bonds, our metals are able to substitute those. That's the power of the cross-coupling, is that it's going to take a leaving group on an sp2 or sp hybridized carbon, and it can create a new carbon-carbon bond. It can do this substitution directly. So there have been so many Nobel Prizes awarded for these reactions. Like, they are so important that like the highest prize attainable in chemistry, the highest award you can possibly earn, the Nobel Prize, they're given out by the dozen for these. Well, they're not dozens, but by the ones, because I think it was like 3 or 4. But there are a bunch of them. That's a lot. That's a lot of Nobel Prizes for these cross-couplings. So we have our Heck reaction, which is specifically looking at bringing these two alkenes together. So it uses either nickel or palladium, and it just clicks these two carbons together. Where you have that halogen, it gets replaced with a double bond, and it just like snaps them in together. Our Stille reaction, that one is famous for taking an iodine with a tin group. So it's coupling that iodine with the tin, usually having a palladium catalyst, and sometimes you need like copper loaded in there or whatever. But again, it's just bringing these two sp2 hybridized atoms, and it's clicking them together in a substitution type reaction, right? So it's a net substitution, but the mechanism is absolutely not SN2 or SN1. It is multi-step, and it forms a ring. Suzuki is I don't know if it still is, I'm pretty sure it is the #1 reaction run by pharmaceutical companies. So this is the #1 way that our current pharmaceutical companies make their drugs, is using this Suzuki reaction, using this iodine substituent and then attaching it to that boron, and it is now making this new carbon-carbon bond. So the benefit of this is that it's usually using very safe reagents. Having boron is going to be really safe. They try to avoid heavy metals when they're trying to make drugs, so that they don't have to worry about any sort of like toxicity down the road. So that's the benefit of like Suzuki is the #1 reaction that is run by pharmaceutical companies. Sonogashira is famous for specifically doing our double bond to a triple bond using palladium and a whole myriad of witch's brew to bring them together. So these are our various cross-coupling reactions. There are way more than these. Like, there are like books written about these reactions because they are so powerful to make these carbon-carbon bonds, especially on sp or sp2 hybridized, which are really hard just using SN2 or SN1, or impossible with SN2 and SN1. Cool. So you don't need to know the mechanism. I won't even test you on them. I do have some questions in the homework to illustrate how you would use them. So it's in the homework to reinforce it in case you want to use it on the final exam. You are welcome to use it on the final exam, but you won't have a specific question where I'm going to be like, predict the product, where I give you these reagents and I expect you to draw that. That's not happening, right? So it's on the homework so that you can know how to use it if you want to on the final exam. Cool. Any questions about the cross couplings or expectations with that? Sweet. All right, then let's move on to our delocalized pi systems. So chapter 14, our final chapter, is going to be looking at our delocalized pi system. Actually, it's not our final chapter, because our final chapter is actually chapter 3. So the highest numbered chapter is looking at the delocalized, meaning not localized, not in one spot. So delocalized pi systems are going to be the pi systems that are spread out. It's our conjugation. So delocalized electrons are the electrons in 3 or more parallel p orbitals, because it's always got to be through those p orbitals, that are participating in some sort of pi type overlap, just meaning that they're parallel. It's like this is redundant. And therefore, they're sharing by at least 3 atoms. So it's where we get these parallel pi bonds. And it's where we're thinking resonance, right? So it's essentially, if you're imagining, like, there are my 3 sp2 hybridized atoms, and I can get that pi bond to move over. It's doing the same thing. It's those 3 parallel, unhybridized, normal p orbitals. Those are the conjugation, which is that orbital overlap through our delocalized, or through the unhybridized p orbitals, the delocalization of the electron density. And the reason that we want it is because it makes everything more stable, makes it lower in energy. So if we're looking at something like where I have this higher energy, lower energy, if you can get here, this would be the conjugated form. Where you can have that delocalization, where you can get that resonance. So our example here is exactly what we actually just drew up there, is that we're imagining you have these 3 p orbitals that are all parallel to each other, so that then when we see the product, or not the product, but the other resonance structure, the reality is the hybrid, right? The hybrid is where we have that electron density equally shared across those 3 atoms, because they are all talking to each other. They're all those p orbitals talking to each other. So the electrons are equally being shared across all 3 atoms, right? It's the average of them, not one individual structure is correct. It's the average that is the reality. So when we have 2 or more double bonds, we're going to be called a polyene. Poly meaning many, ene referring to our alkene, so double bond. Polyene is actually going to be a more general term, referring to if you have multiple double or triple bonds, we'll call them all polyenes. So it's just going to be describing anytime you get multiple pi bonds across multiple atoms. So we have 3 ways of describing our polyenes. We have cumulated, conjugated, and isolated. Cumulated is going to be where they are right next to each other, where you're going to have 0 sigma bonds in between your pi bonds. So that's cumulated. That dot is representing a carbon. It's there to illustrate that I didn't just draw an obnoxiously long alkene. The dot is really breaking it up to indicate that like these are 3 elements there. Like there's carbon, carbon, carbon. That's the point of that dot. Cumulated alkenes are also known as allenes, which you remember last time we talked about them was when we talked about our stereochemistry, and we said that this was our exception to that chiral molecule, where we had said normally you need to have a chiral atom in order to have chirality at the molecule level. The exception was our allenes and also our binaphthals, but it was that allene because it had those perpendicular pi bonds. There's no resonance here. Those pi bonds are perpendicular to each other, and so then that is going to give it that rigidity of like 4 quadrants to be able to be chiral. So there's no resonance because these p orbitals are like this. That central atom is sp hybridized. These are linear. So cumulated is when you have 0 sigma bonds between your pi. Conjugated is going to be where you have 1 sigma bond between your pi. So we get this like double, single, double, or it could be triple, single, double, or triple, single, triple, whatever. It's where you have those 1 sigma between your pi bonds. There's that separation. Isolated is going to be where, think like isolated, like it's on an island, like they are alone. They don't even know the other one exists. This is just, there are 2 alkenes that happen to be on the same structure, but they are so far apart. So our isolated is going to be where we are separated by 2 or more, so greater than or equal to 2 sigma between our pi. So this is saying that those double bonds or triple bonds, they're not talking to each other at all. They're just totally, they're just 2 that happen to be on the same structure. They don't know the other exists. They don't care that the other exists. We are going to focus on those conjugated systems because isolated is just going to act like normal alkenes. Or alkynes, right? So it's acting just like a normal double or triple bond. Cumulated are also essentially kind of acting like a normal alkene because, again, the pi bonds aren't actually talking to each other. They just happen to be really close. Conjugated, that's where our pi bonds talk. Now they're going to have this delocalization. Now the electrons are going to be spread out. So conjugated is that special situation. That's why we're going to talk about the conjugated. What happens when I have a conjugated system? So some properties of our conjugated system, that central bond, that central sigma bond, is shorter than a normal sigma bond. So if I think of that versus this, that sigma is the result of sp2 orbital overlap. Whereas this sigma is a result of sp3 orbital overlap. So if I have more S character, less P character, that brings my atoms closer together, right? It makes the orbitals smaller, so then all they are brought closer together. So that's why it's shorter. That also then means that it is stronger, because it is, the closer you are, the stronger the bond. The shorter the bond, the stronger the bond. So it is going to be closer together. Our conjugated dienes are going to be unusually stable. Like, it's going to be weird how stable they are. So if I draw this energy diagram, so that I just have substrates here. I'm going to just draw molecules. But my energy is on the y-axis. So if I look at just a normal cyclohexene, so I'm imagining my x-axis is cyclohexane. So these are all relative energies. So I'm going to say my alkene here, that's this amount of energy. Oh, I don't remember what the number is. It doesn't matter. We're going to call it X. I don't actually care if you know what the number is. It's in the textbook, but whatever. So if I have that single bond, then that is going to be, oh, I wonder if it's over here. Nope, still not. Okay. I expect it to be some amount of energy. If I get two alkenes and I become that isolated, an isolated diene, di meaning two, then I am 2x, because I have two double bonds, so I'm twice the amount of energy. Our conjugated dienes, though, are lower in energy. It is going to be less than 2x. I don't actually know what the numbers are. It's like, I want to say this is like 120, 240, and this is like 200, I think. Kilojoules per mole. I don't actually remember. But the point is that it's less. So it is this weird stability getting to have that double single double that is lowering that energy down. We're also going to see unique reactivity with them. So if I think about this alkene addition, what is the product of this reaction? Yeah. Yeah, it's 2-chloropropane. So this is our carbocation mechanism. You see strong acid, carbocation, and then it is going to be that Markovnikov addition. So our mechanism is that our alkene attacks the acidic proton, and then because that's a base, we show it's reversible. We make that carbocation. You put it on the more substituted side, because you always got to make the most stable the most stable carbocation possible, and then the nucleophile attacks. So this, another way of describing this product is that it's 1-2 addition. Because we added a hydrogen onto carbon 1 and a chlorine onto carbon 2. So it is considered 1,2 addition. With our conjugated additions, with our conjugated dienes, we're going to also be able to have that 1,2 addition, but we're going to get another product. So if I look at just normal 1,2 addition, it is just the same deal of my pi bond attacks the strong acid, our bond breaks, we give the electrons to chlorine. I tried to draw the line in there because I'm trying to cheat, but the line's there, that bond is there. So then the chloride can attack that carbocation. And I still get 1,2 addition. Right? That is still possible with my conjugated diene. That I can just act like, hey, here's an alkene. The alkene reacted as if the other one wasn't there. That is one product. What can also happen, though, is that this carbocation can be delocalized. So I can draw a resonance structure where I actually have a primary carbocation and an internal alkene. And then the chloride can attack that carbocation, which, remember, that carbocation is still stable because it's allylic. So it's more stable than having just a normal tertiary carbocation, right? Having that resonance makes it more stable. So I'm able to attack either carbon 2 or carbon 4. So that's the other product that we see, is that 1,4 addition. And we get both with our conjugated diene. You see both products. Both are formed. Usually, one-4 addition is the major product. But must check reaction conditions and carbocation stability. The reason why 1,4 is usually the major product is because it leads to a more stable alkene, right? Do we see that this is our di-substituted alkene as opposed to a mono-substituted alkene? So usually this product is more stable. So we're going to call that, whenever we look at the more stable product, we say that it is the thermodynamic product. The one that is going to form more quickly is going to be our kinetic product. So our kinetic product is going to be the one where it's more focused on the carbocation stability than, and it's usually just doing a 1,2 addition, is you make that carbocation and then it reacts right away. That's the kinetic product. If you care more about the stability of your alkene, that is your thermodynamic product. All right, we'll talk more about that next class. Have a wonderful day.